What are the strengths of being a polyglot developer?
Welcome to the Hello World Show. I'm Spencer Schneidenbach.
I'm Heather Downing.
And we're here at Detroit.Code with Ted Neward. Ted Neward is an author, blogger, speaker, and director of developer relations at Smartsheet. Or, summed up, he is one big geek, as he calls himself. Welcome to the show.
He's a dude. Thank you. Thank you for having me.
All right, Ted, what are you going to teach us today?
So one of the things that people frequently talk about is the idea of being a polyglot developer, the idea of learning multiple languages. So I thought I would go with a little concrete example thereof. So imagine for the moment, you guys are familiar with programming languages like C#, Java, etc., right? We have concept of a collection, right? So we'll just create a collection here, 1, 2, 3, 4, right? Using angle brackets, standard, array type syntax. So one of the things about Haskell is it's a functional programming language. And Haskell actually has this concept of a list, which literally looks, let x's, it's a very common way to refer to a list, equal to 1, 2, 3, 4, right? It's a very simple list. We can do various things with this list. We can do something like head x's, which just peels off the first element. We can do tail x's, which says take off the head and return the rest. We can do like first x's, which just gives us, the value 1, et cetera, et cetera. We can basically peel things off of this particular list. One of the other things we can do with these lists, for example, is we can actually take some number of elements off of this list. So take 2 of x's gives us 1 and 2 and leaves 3 and 4 remaining, right?
Yeah.
So far so good, pretty straightforward stuff. Now, one of the other things that Haskell will let us do with these lists will actually, rather than having to specify each element individually, we can actually specify a range using the range operator, just the straight dot dot. And this says, give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or in some cases, we can do 1, 2, 4 up through 10, which now says, give me 2, 4, 6, 8, 10, right? Now, this is actually an abstraction of a larger concept which says, let me actually do some simple calculation as a part of producing the next value. So this could actually be something like x, where x is whatever times 2. Right?
Okay.
This is sometimes referred to as a comprehension. And my Haskell syntax may be a little off, but the idea is each time I go to this list, I'm going to try to get some value times 2. Which leads us into the next idea, which is the idea that Haskell can actually give us an infinite list. Now, reasonable question to ask at this point is, why in God's name would you ever want an infinite list? This is kind of like, seriously, this is academia run wild. We would never actually have an infinite collection of things, because particularly if you're coming from the world of C# and Java and whatnot, we are constantly thinking of these things as collections, and collections by definition are bounded, right? In C#, when we do a for each, right, var x in x's, we're basically saying give us an iterator object that goes over each element in this list, and we will spin through this loop until we run out of elements in that list. If we never run out of elements, this is what we sometimes refer to as a bug, right? And why would you ever really want to have that in your code as a deliberate concept, right? So we'll just put that off to the side for the moment. Now, the interesting thing is this concept here, or the comprehension concept, et cetera, is something that we do see in C# from the standpoint that we do have functions that can do yield return, right? So imagine for a moment I have some function, we'll call it foo, and we'll do a while true yield return some random number. And you look at that and you say, wait, what? Why exactly would this work? Well, effectively, the yield return statement in C# is the way in which C# is able to produce comprehensions, or what the JavaScript folks call a generator, right? If this were JavaScript, it would be function star, and we would say yield Heather, yield Spencer, yield Ted. Okay? What happens in each of these cases is yield return or yield, this is C#, this is JavaScript. This is effectively a return, but it's a return inside of a state machine. So effectively what's happening here is this thing, if you look at the generated code, if you look at the generated IL in C#, or if you follow this inside of a JavaScript debugger or whatnot, first time you call this thing, we'll return the string Heather. Second time you call this thing, we return the string Spencer. Third time you call this string, we return the string Ted. Fourth time you call it, nothing left to call. So that we can do a while or a for over this function call. And effectively what it's handing back is an iterator or an enumerator in the case of C#, which we can iterate through until we run out. Now in this particular case, we're just going to keep going and generating infinite random numbers until, well, until we run out of random numbers, which will be never, right? So this is all kind of interesting in sort of an academic sense. But let's assume for a moment, right, that we have a series of things that we can do with one of these lists, right, with one of these infinite streams. So let's say let E equals get some value from that random number generator, right? So that will return to us a random number, and then we can process this thing and then say, let's go get another one, E2 rand. We'll just go get another one, because each time we call into that thing, remember, even though it was a while true, we hit the yield return, we immediately yield back the value. We can now go on and process it, right? So it's not really an infinite loop, but it kind of sort of is, but kind of sort of not, but it's kind of sort of is, which here, if we were trying to generate an infinite collection, this would obviously crash memory. What Haskell is doing is behind the scenes, this is turning into a function that knows how to produce a number. That's basically what this is. That's basically what the JavaScript example is. In each case, we have a function that knows how to produce the next value on demand. In other words, what Haskell is teaching us is that iterators don't necessarily have to be associated with collections, that an iterator can stand alone and produce the next value out of thin air. And you say, okay.
Why would we use this?
And who cares about this? Because that doesn't seem like a particularly useful thing, because all the collections, all the things we would ever want to iterate over are always bounded sets of data, right? Until they're not. So think about this. This is your architecture. I don't care what kind of project you're building, it's always this. Box, arrow, cylinder. This is the universal software architecture for every project ever designed. In our particular case, this will be, say, a web browser. This will be a web server or an API server, and this, of course, is your data storage, right? And communication always flows from left to right, right? Always. There's never a scenario where we actually want to push it from right to left, right? There are always cases where somebody says, gosh, if I'm currently building an e-commerce portal and I want to keep track of the number of items that somebody has in their basket, I actually want the database to feed some of this to the left, right? I actually want to go inverse to this. Well, this is where people start building WebSocket tunnels to go back here, which then, you know, they do something similar here, some sort of stored proc, callback, whatever, in order to be able to feed this direction, which means now inside of your web browser, you have to think about, how do I deal with data that's coming through over here? It could be one event, it could be 0 events, it could be a whole stream of events. It could, in fact, be an infinite stream of events. So now, once we start acknowledging the fact that there is a whole bunch of things, such as mouse clicks, such as button presses, such as scroll, when the user is scrolling up and down, et cetera, you actually begin to see that these are, in many respects, an infinite stream of events. And once you start looking at these as a stream of events, that these are effectively iterators without collections, there's no collection of scroll events that's hiding out in the browser. It's generating them as the user is moving the mouse around or sliding the scroll bar up and down or whatever. So these are a stream of events that you may choose to consume or not, as the case may be, but now it's just a list. And if we now have functions that say, let me take the first event off of that list and pass that as a parameter into some function which uses that event, does some sort of behavior, then the next time around we'll take the next one off that list, and if that list has nothing, we can just block. And this, all of this infinite streams concept coming from a variety of disparate sources is what the world is referring to as reactive programming. So once you understand Haskell's infinite lists, never have to write a line of code in Haskell ever, but the concepts that are built into that notion of list processing, concepts of taking a function, processing it intrinsically statelessly with no side effects, et cetera, congratulations, you can now put reactive on your resume. So when we talk about doing queries, I mean, even when you look at straight SQL queries, right? When I say select star from table where, that's one of these filter criteria to restrict the set of. All right, now this is not a table. Now this is the set of user events that are being generated by the browser. And so now I can take those set of events. And remember, right, despite the fact that in a SQL database, it's a bounded query, so we can look at that full set and then filter from there on the server. These are coming one at a time through a stream. But we can filter on it and say, unless this event is a mouse event, and we can actually filter it even further and say, this is a mouse event within this particular bounded area of the screen, then perhaps we'll do another map to it to turn it into some other bit of data, which we can then hand off to some function to process and whatnot. This notion of applying this style of reactive programming to the user interface is actually the subject of a very fascinating user interface framework called Elm.
Yes.
And even if you look at the Haskell language and you say, I will never use this in a production environment, just the fact that you start to see how they view the world and how they interact with it, a world without objects, it's still a very, very viable world. And even if you have objects, you might start to see things in a very different mindset. For so many years, we've been living in the object world where everything is about nouns. The functional programming world is about verbs. And funny thing about most language, you need both nouns and verbs to in fact be clear. So perhaps the object world needs to be a little less noun-centric, and the functional world can be a little less verb-centric, and there is sort of a happy medium in the middle, which is where languages like F# if you're a .NETer, or Scala, or Clojure if you're a Java-er, and so on and so forth, can actually come in and play some really, really powerful effects. Even if you never use these languages in your production code base, having been exposed to them, having understood some of the concepts behind them, you will never quite program the same way again, and in most cases your designs will be a lot clearer for having learned some of this stuff.
Nice.
Yeah, I've found for me personally that learning about functional programming has definitely influenced how I write C# every single day.
And there's so many additional concepts beyond functional programming, right? Learn dynamic programming. If you've never played with Smalltalk, you really owe it to yourself to play with Smalltalk, because that is object-oriented the way the guy who invented object-oriented intended it to be. We have a quote from him along those same lines. Alan Kay, I invented the term object-oriented, and I can tell you for a fact C++ was not what I had in mind. There's a tremendous amount of value in looking at some of these languages that, for example, Smalltalk is about dynamically typed objects that only do message passing. So go and look at some of how they approach the world, and you see that they model things very, very differently than the way that the traditional objectists do. And then bring that back to your C# code, and discover that C# has a dynamic keyword, which actually will allow you to do some of the same things that, for example, Ruby on Rails will do. There is an interesting web framework called Oak that's been out for several years by Amir Rajan out of, I think it's Dallas, Improving Enterprises, Improving Technologies, Improving something. I forget the exact company name. But Amir basically looked at Rails, said there's some really fascinating dynamic stuff we can do there, and applied it to C#. And so if you're building web applications and you're kind of excited about Rails, but your company doesn't want to get off the .NET stack, here's a nice halfway point to be able to do that.
Thank you so much for giving us kind of a tour around how much these languages could have in common, and maybe we don't look at it that way. So we appreciate it so much.
Yeah, thank you.
You're very welcome.
Don't forget to share this video on social media.
And comment below to be entered into our weekly giveaway.
Tell us what questions you have for our guests. See you next time.